right, let's take a look at page 191. We're just going to kind of finish the conversions we did yesterday, and then we're going to get into the calculus of these polar graphs, how we can find derivatives. You're going to see how they're very familiar to the parametric ones that we did before, and you guys seem to do really well with those. So I think today's going to be kind of easy. And we don't really have a lot to cover, so yeah.
Can I do my locker?
Yeah, go ahead. We'll wait till she gets back.
Sorry.
It's okay. All right, so yesterday we left off converting these rectangular equations into polar equations, and we mostly utilized at the top these two x and y equations because we had to convert x's and y's to r's and thetas. The bottom three, we're going to go the other way. We're going to convert polar to rectangular, so we're most likely going to have to utilize these two to help us convert r's and thetas to x's and y's. Okay, so our first one, we'll have r equals 2 cosine theta. How might you want to use those two options at the top? I know you can't see them on the board, but they're on your paper. How might you want to use those two conversion equations to help us convert this polar into rectangular? It's okay. Can we replace r with something? Can we replace cosine with something? All right, so that comes from our Pythagorean theorem. Remember, r is the radius or the hypotenuse of that triangle we create. And then how can we replace the cosine of theta with like some type of x and y? Maybe we don't necessarily have to use just these two. Maybe we can utilize these ones as well, because we have 4 options that relate either x and y and theta somehow, or r.
For the cosine, can we plug in like x over r?
There you go.
Instead of writing r, can we just put like the square root of that?
Well, let's see. Okay, so we have cosine of theta. If you were to divide the r over, we can get cosine by itself, so x over r. So we'll go ahead and plug that in here. And again, instead of the r, you wanted to replace it with that square root. Okay, so we'll have the square root of x squared plus y squared equals 2 times x over the square root of x squared plus y squared. So I like how all the r's are gone and all the thetas are gone. We just have x's and y's. Can we kind of clean it up a little bit, make it look a little prettier?
You can multiply into 2 and that's just going to go on top.
Okay. Okay.
Multiply it by the stuff on the bottom.
To the other side?
Yeah.
Good. Okay, so notice how the square roots match. So if you multiply a square root by the same square root, the square root would go away. So we're left with x squared plus y squared equals 2x. I say that's pretty cleaned up. We don't necessarily have to solve for y. If you take a look at the 3 from yesterday, I know the first 2 said y equals, but notice how the third one did not say y equals. It was x squared plus y squared. So I think we can leave it like that. I say that's pretty good. what about the next one? This time we just have a theta. Theta equals 3/4 over 4, or 3 pi over 4. So somehow we have to change that theta into an x and a y.
Can we put 3 pi over 4 into the tangent?
Mm-hmm. So tangent 3 pi over 4 equals y over x. Good. Notice how the theta's gone, and we have y's and x's left. But we could probably, again, clean it up, simplify it. Can we think about what the tangent value at 3 pi over 4 is? Let's see, on our unit circle, 3 pi over 4 is in the exact middle of the second quadrant. -1, good. So maybe we'll multiply the x over, and we'll get negative x equals y. Perfect. All right, what about the third one? R equals cosecant theta. Any ideas? Okay. So that got rid of the r. Somehow we gotta get rid of the theta. What is cosecant? Say it again? It is 1 over sine. So maybe instead of cosecant, we'll write 1 over sine. They mean the same thing. So maybe that'll help us out because we have those conversion equations that deal with sine and cosine, not necessarily cosecant. So what do we want to try from here?
You solve for sine, like sine would be y over r, and then if it's 1 over sine, it would be like the reciprocal.
There we go. All right, so sine, oh, sorry, at the top. We can solve for sine. We get y over r. So this would be 1 over y over r, but that would just in turn make it the reciprocal. So we would have r over y. Kind of running out of room here. Maybe I'll go and work up here. Hopefully you guys have enough room. So far so good. We still have an r though. We just want x's and y's left. Okay. All right, so let's see, can we solve for y? Do you notice anything that's gonna happen or kind of cancel, maybe? What do you think, Cameron? Yeah. You get 1. If you do a little switcheroo with those, multiply the y over, divide the square root, the square roots would cancel because you're dividing something by itself, so looks like y is 1. There we go. We doing okay? It's a little kind of algebraic manipulation. You got to do some substitution, simplifying. Eventually we'll be able to make the conversion. Okay, so let's finally get into the calculus. So when we talk about the slope, aka derivative, slope of a tangent line for polar equations, these are going to work very similarly to how we had the parametrics. Remember how parametrics we had x equaled something with t in it and y equaled something with t in it? Now we have x equals r cosine and y equals r sine. So we're going to utilize those two kind of conversion equations specifically to help us with these derivatives. Now, if you take the derivative of x, remember r is going to be a number because that's representing the radius, how far you walk out from the pole. and your variable is theta. So whenever we take the derivative of this x equation, we would write dx over d theta, because theta is that independent variable. Similarly for the y, we would have dy over d theta. When we did parametrics, we had dx over dt, right? And dy over dt. Now we just have something over d theta, because that's our new independent variable. And very similarly to how we did derivatives for parametrics, we can figure out the slope of the parametric curve by simply taking the y derivative divided by the x derivative. Remember how we did that for the parametrics? It's going to work the same way with these polars. Okay, so it's not really anything new, it's just, or it's the same process or similar process that we did for parametrics just for these polars. So let's check out this first one. Find dy over dx and the slope of the graph of the polar curve at the given theta value. So notice how they give us the polar equation, r equals 2 plus 2 sine theta. Can we think about what shape this graph might be when we went through all those different graphing examples the last 2 days? I know we did a lot, but can we think about what this shape might look like? Maybe we'll try to draw a little picture of it. What do you think, Cameron? It's going to be a cardioid, so we're going to have that heart shape. And can we think about where or how this heart shape is oriented, where it might be located? This one was a little tricky. You had to take that addition number and then the coefficient number and do something with those two. Can you find it?
Up 4.
Okay. Upside down heart. Okay, so it's up 4 on the y-axis, because if you do 2 plus 2, you get 4, and sine represents a y value, so you're on the y-axis. If you do 2 minus 2, you get 0, so the other side of that heart is at the pole or the origin, so we are going to have that upside down heart shape. So there's our graph. All right, so let's see what we can figure out for the derivative and then the derivative value at this specific spot. And maybe we'll come back to the graph to make sure that our answer kind of makes sense. So in order to figure out dy over dx, we have to first figure out the derivative of the y equation that has theta in it, but also the derivative of the x equation that has theta in it. Notice how x is r times cosine theta. So how can we officially write the x equation given this polar equation or curve? We need x equals r times cosine. Can we rewrite that somehow? Do we know what r is specifically for this example? Isn't r, the radius is that polar curve they give us? So instead of this r, we'll just replace it with that 2 plus 2 sine theta they give us. But we have to multiply that by cosine. So maybe we'll go ahead and distribute in that cosine. All right, let's do the same thing for the y equation. y was r times sine. All right, you can either put the squared after the sine, like sine squared theta, or if you want to put sine in parentheses and then square it, you could do that too. They mean the exact same thing. We did okay so far? We have the x equation and the y equation. So what we got to do now is take the derivative of each one separately, and then we'll just combine them at the end to get our overall derivative dy over dx. So let's check out the x derivative first. This would be dx over d theta, because notice how our independent variable is theta. So we're just going to take the derivative as we work across our equation. We need the derivative of 2 cosine. So that would be negative 2 sine theta. And then how do you want to take the derivative of the next term? We have 2 cosine times, or 2 sine times cosine. Good, Abby. There we go. We have our product rule. All right, so 1 we'll say is 2 sine theta. Derivative of cosine, we have negative sine plus 2, and then we need d1, so the derivative of 2 sine is 2 cosine. Perfect. All right, let's clean it up. So we have negative 2 sine theta minus 2 sine squared theta plus 2 cosine squared theta. All right, so there's our x derivative. Let's check out the y derivative. So we need the derivative of 2 sine, which would be 2 cosine. And then how might you want to find the derivative of the next term? 2 sine squared. What derivative shortcut can we use there? Go, Cameron? The chain rule, right. So let's bring down the 2. That'll change to a coefficient of 4. We keep the inside of sine. Our new power would be 1. So you don't have to write that if you don't want to. But we got to finish off the chain rule by multiplying by the derivative of the inside, which would end up being cosine. We still good with our derivatives? Our shortcuts? Good. All right, so now that we have the individual derivatives, let's go ahead and write the overall slope of the curve at any point. We need the y derivative divided by the x derivative. So far, so good? All right. They also wanted us to evaluate this slope of the curve at pi over 2. So let's see how that works out. So we need 2 times cosine of pi over 2. Using our unit circle, that would be 0. Plus 4 times sine of pi over 2 would be 1. Times cosine of pi over 2, which is another 0. All over negative 2 times sine of pi over 2 would be 1 minus 2 times sine of pi over 2 is 1, and then we'd have to square it, so that's still 1. And then plus 2 times cosine of pi over 2, which would be 0. Square 0 is still 0. So it looks like we get 0 over -4, which would be 0. So what's that telling us about the curve at that spot of pi over 2? If it has a slope of 0? Can we analyze that? Or interpret that? What does the slope of 0 represent? Horizontal line, okay, it could be a level spot or a max or a min, but you have that horizontal line. So if we take a look at the curve that we drew, pi over 2 would be up here, right? If you think about your unit circle, you have 0, pi over 2, 3 pi over 2, or pi and then 3 pi over 2. So at the pi over 2 spot, if you were to draw a tangent line, notice how it would be flat. That's what we were analyzing. That's what we were finding or figuring out at that particular location. So it looks like we did everything correctly. We figured out the x and y equations correctly. We found the derivatives correctly. We evaluated it correctly because it's completely making sense. We did okay? So I didn't put a lot of examples on this because, at least in my opinion, correct me if I'm wrong, this is very similar to the parametrics that we did. So I think it's an easy connection for us to make. Is that okay? All right, so that's it for this section. We'll stop there because we're missing some people, and we'll pick up with polar graphs again maybe tomorrow. We'll see who's here and who's not here. Okay?